Okay, so I messed up there a little bit on that last video. So let's make sure you understand that power of the reactor is going to be proportional to the macroscopic cross-section for fission times the thermal flux, where we said that the macroscopic cross-section is equal to, well, the microscopic, which is just a property of whatever our fuel is, and the product of the atomic density. This equals that. So we know that macroscopic cross-section for fission is going down over core life, and if I want to maintain power, maintain the same reaction rate, I'd have to increase my thermal flux, all right? Now, we know that when the neutrons are born, they're born fast. Neutrons are born fast. Both the prompt and the delayed were born fast. So we send these on a journey through what we'll call the land of moderation, the land of slowing down. So all of our neutrons, both prompt and delayed, are born fast. We send them through the process of moderation, and then they slow down to slow neutrons, which, for our sakes, would also be thermal neutrons at equilibrium with its surroundings. Great. Well, at any given time, I may have fast neutrons if I'm looking at a certain spot, or slow neutrons / thermal neutrons. So I have a certain fast neutron spectrum. And if you'll think about how a boiling water reactor works, I have the reactor and I have my core here. There's the core. And we know we have jet pumps here. Water travels like this through the jet pumps. And then we'll find out that water starts to boil right about there. And then I have a water-steam mixture here. So what we can say is the moderator at the top versus the moderator at the bottom is different. I have lots of water at the bottom. I have a very effective moderator. But once I've heated it up and expanded those neutrons into expanded the hydrogen molecules, the water molecules and the hydrogen with it way out, well, they're very far apart. The slowing down length and the thermal diffusion length is changing as we heat up our moderator. So I'm changing the characteristics of my moderator from the bottom of my core to the top of my core. So I can tell you that I will have a faster energy spectrum at the top and a slower energy spectrum at the bottom for my neutrons. If you'll think about that, that's going to be very key as we move forward. We will tend to have a faster energy spectrum at the top of our core because our moderator is heated up and changed phase into steam versus the bottom section of our core where we will have a very effective moderator and a very slow or thermal neutron flux pattern. Here I'll have a fast neutron flux, and down at the bottom I'll have a slower neutron flux. Very key. So when we talk about neutron flux, we can talk about where the flux is located. We can talk about, as I look at the entire core, I'll just put a right circular cylinder here. This is the core that I just had. I'll actually put a boiling boundary. We could talk about how fast or thermal neutrons are divided. I would expect more thermal flux here below this boiling boundary where I know that there's water. Here there's steam. So I would expect up here to be they're more of a fast flux, right? This will be a fast flux. And then I can talk about how flux is located across the core or up and down in the core. When we talk about how flux is made from the center outward, we call that radial flux. So that's the flux like this, from here to here across the core. We can also talk about how power is made from top to bottom, bottom to top. We call this the axial flux. So that's here to here. Right? So there's an axial flux profile that can be affected under certain conditions and a radial flux profile. And as we move forward, you need to understand what we're talking about. When we talk radially, what's happening to the neutron flux across the core this way? When we talk about axial flux, what's happening to the axial flux, the neutron flux population up and down? So, some notes. Over core life, looky here. The macroscopic cross-section uranium-235 is going down. Therefore, if you want to maintain power constant, we must obviously increase thermal flux. Right there shows that the power of the reactor is proportional to that macroscopic cross-section multiplied times the thermal flux. So if this is going down, this must go up. How is it accomplished? Rods and or recirc. Here's a K&A. Describe fast flux, describe thermal flux, and describe thermal flux distribution. Well, this picture here shows a radial flux distribution and shows an axial flux distribution. And we can talk about how there's a higher probability to have a fast flux in the upper portion of the core and a lower energy level flux or a thermal flux in the bottom of the core. That takes us to a couple more practice questions, and then that'll be neutrons. Send your questions in on this one because this is vitally important in terms of understanding and going forward with the rest of the chapters. Got to know as much as we possibly can about neutrons.